We speak of time as if it were a river. Time flows. The years pass. The future approaches. The past recedes. These expressions feel so natural that we rarely notice the strange question hidden inside them. If time flows, what does it flow through? A river can move at several meters per second. But how fast does time move? 1 second per second. That sounds correct, yet it explains nothing, because we have used time to measure time itself. Look at a clock on a desk. Its second hand moves and its numbers change. We say that the clock shows time, but what it directly shows is a gear turning, a quartz crystal oscillating, or an atom undergoing a regular transition. A clock may not be a detector that receives an invisible substance called time. It may simply be a device that compares one kind of change with another. Then where does our certainty that time is flowing come from? Why do we feel that the past is gone, the future has not yet arrived, and only the present is real? Does physics recognize this feeling as a fundamental feature of the universe? Today we will travel from Newton's absolute time to Einstein's relativity, from entropy and memory to the problem of time in quantum gravity. Near the end, we will carefully examine a speculative information gauge, or IG, perspective. Could time emerge as the ordered updating of informational relationships, and could that idea ever be tested? Let us begin in Newton's universe. For Newton, time was like a vast cosmic clock. Whether a star exploded, a person fell asleep, or nothing happened at all, time continued at its own uniform rate. In principle, a clock on Earth, a clock on Mars, and a clock on the far side of the galaxy could all be synchronized. There was one absolute now, like a single photograph of the entire universe. This picture fits everyday life remarkably well. When it is 9 in the morning in one city, it is 9 according to the same standard time in another. When we throw a ball, drive a car, or calculate a planet's orbit, Newtonian time is an extraordinarily accurate approximation. For centuries, time looked like an invisible background, a stage on which events unfolded. But that stage began to fracture when physics accepted that the speed of light is the same for every inertial observer. Imagine a very long train moving at high speed. Lightning strikes the front and rear ends of the track. A person standing at the midpoint of the platform receives both flashes at the same moment and concludes that the two strikes were simultaneous. The observer inside the moving train is heading toward one flash and away from the other. Because light still travels at the same speed in both directions, that observer concludes that the strikes did not occur at the same time. This does not mean that one person was fooled. Observers moving relative to one another genuinely disagree about the simultaneity of distant events. The single now shared by the entire universe disappears. This is not merely a philosophical trick. A clock that travels rapidly along one path can be reunited with another clock and show a different elapsed time. A clock deeper in a gravitational field also runs differently from one higher up. Satellite navigation systems must correct for relativistic differences in order to remain accurate. Relativity does not say that time is unreal. Proper time, the time measured by a clock along its own path through spacetime, is a real physical quantity. What relativity removes is one universal time ruling over everything. Measured duration cannot be separated from motion, gravity, and the route taken through spacetime. This is where the famous idea of the block universe appears. Think of a map of a city. The map contains the starting point, the destination, the streets already crossed, and the streets not yet visited. In a similar way, spacetime can be pictured as a four-dimensional map containing events. We live along one world line within that map. Instead of the past vanishing and the future coming into existence, events may occupy different locations in space-time. In this view, the present is not a glowing line sweeping across the whole cosmos. Different observers slice space-time into nows in different ways. This has led some physicists and philosophers to suggest that temporal passage is not an objective property of the world, but part of the way conscious observers experience events. But caution matters. Saying that relativity fits naturally with a block universe is not the same as proving that one metaphysical picture is uniquely true. A map containing an entire path does not erase the traveller's walking, decisions, or experience. Physics strongly constrains the relationships among events, but it does not automatically explain why we experience one present moving into another. For a clue, we must look at a broken cup. A cup falls from a table and shatters. We never see the fragments spontaneously leap from the floor and reconstruct the cup. Hot coffee cools. Perfume spreads through a room. Living bodies grow older. In all these processes, we recognize a direction of time. The puzzle is that many microscopic laws of physics work almost equally well when their time direction is reversed. If the velocities of all the molecules could be reversed with impossible precision, Nothing in the basic equations simply forbids perfume molecules from returning to their bottle. Why then do we never observe it? Thermodynamics points to entropy. Calling entropy disorder can be useful, but it is incomplete. More precisely, entropy reflects how many microscopic arrangements can produce what looks like the same macroscopic condition. Perfume molecules clustered in one corner of a bottle form a possible but very special arrangement. Those molecules spread throughout a room can be arranged in overwhelmingly more ways. A system therefore moves with near certainty from an unusual macrostate with few compatible microstates toward an ordinary macrostate with many. The cup does not fail to reconstruct because reverse motion is forbidden by a new force. It fails because the motions of an enormous number of particles would have to line up with unimaginable precision. This asymmetry is what we call the arrow of time. In the direction we label the past, the universe had a remarkably low entropy condition. Toward the direction we label the future, entropy increases. Yet this answer creates another question. Why did the early universe have such unusually low entropy? Thermodynamics explains why an arrow follows from a special low entropy beginning. It does not, by itself, fully explain why the universe began in that condition. The arrow of time is also deeply connected to memory. We remember yesterday, not tomorrow. It feels obvious, yet physically it is a profound asymmetry. A memory is not a transparent movie placed in a non-physical drawer. Neural connections change. Proteins move. Electrochemical states are altered. A camera sensor and memory chip consume energy to record an image. A fossil requires a body to interact with sediment and leave a durable structure. Making a record releases heat and increases entropy somewhere. Memory is a physical trace with a thermodynamic cost. The alignment between the direction of memory and the direction of increasing entropy may therefore be more than coincidence. What we call the past is the direction that has left records in the present. What we call the future is the direction that has not yet produced records here. In a more unsettling sense, we never directly encounter the past itself. We read present traces, the current state of a brain, a photograph, a letter, a fossil, or arriving starlight. The star we see may belong to the distant past, but the act of receiving its light occurs now. The past is gone, yet it remains correlated with the present. The now we experience is also unlike a mathematical point with no width. When we listen to music, the first note has already faded by the time the next one arrives. Yet the mind holds them together within a short window and hears a melody. If the present were experienced as a dimensionless instant, music would collapse into a series of isolated sounds. The brain integrates recent traces with incoming sensation and constructs a psychological present with a certain thickness. This also helps explain why time can feel fast or slow. During an unfamiliar journey, many distinct events may be encoded in memory. Looking back, the period can seem long and densely filled. A repetitive routine may leave fewer distinctive markers and later appear compressed. During danger or tedious waiting, however, attention can focus intensely on duration, making the immediate moment feel unusually long. Time as experienced and time as remembered do not stretch in exactly the same way. None of this is relativistic time dilation. A person in deep concentration does not make an atomic clock run faster. Proper time measured by a physical clock and subjective time constructed through attention and memory must remain distinct. But the difference tells us something important. The feeling of passage is not contained in clock readings alone. When memory and attention build a narrative on top of physical sequences, we experience that narrative as a moving present. Could it be that time does not flow, but records accumulate? Could the feeling of passage arise because the universe continually creates traces that are extraordinarily difficult to reverse? Quantum mechanics makes the question even deeper. In standard quantum theory, quantities such as position and momentum are treated as observables. Time usually plays a different role. It is supplied as an external parameter. A laboratory clock tells us how much time has elapsed, and the theory predicts how the quantum state changes relative to that reading. This framework works spectacularly well in experiments, but it becomes troublesome when we attempt to describe the entire universe as a quantum system. There is no clock outside the universe. The clock, observer, and apparatus must all be contained within the system being described. In general relativity, temporal coordinates are intertwined with the geometry of spacetime, and physics must remain valid under changes of coordinates. In ordinary quantum mechanics, an external time parameter directs the evolution of the state. When we try to combine the two theories, these roles do not fit together easily. This is known as the problem of time in quantum gravity. In a famous approach represented by the Wheeler-DeWitt equation, the wave function of the universe does not explicitly contain the familiar external time variable. On the page, the universe can look frozen. Does that mean no star is born, no person ages, and no clock ticks? Not necessarily. A whole that appears stationary can still contain changing relationships among its parts. Don Page and William Wootters proposed a relational picture sometimes described as evolution without evolution. Divide the universe conceptually into two parts. Use one as a clock and the other as the system to be observed. The total state may be stationary relative to any imaginary external time. But when we ask what state the system has when the internal clock shows a particular reading, an apparent evolution can emerge from their correlations. Imagine two strips of film. One records the successive positions of a clock hand. The other records a flower opening. Spread both strips out at once and nothing on the table moves. Yet when each clock image is matched with the correlated image of the flower, a sequence appears. No external river pushes the film forward. Change is reconstructed from relationships inside the film. This idea shows how time might arise from entanglement and correlations rather than from a fundamental background. Theoretical work and experimental simulations of relational quantum clocks have continued to explore this possibility, but once again we should not overstate the result. This does not mean that every aspect of experienced time has been explained, or that a complete theory of quantum gravity has been experimentally confirmed. It is a serious clue, not a final verdict. Another proposal is thermal time. Instead of choosing time first and describing how a state changes, one asks whether the statistical state of a system and the structure of its observables define a natural flow. In this view, time is not necessarily a single axis installed in advance for every possible world. It may depend on the state and on the macroscopic descriptions available to an observer. When physicists say time may be emergent, they do not necessarily mean that time is an illusion. Temperature is not a property of a single isolated molecule, yet it is real, measurable, and indispensable at the collective level. Time could likewise be an effective physical quantity arising from deeper relationships. Emergent does not mean fake. It means that something may not sit at the bottom layer of explanation. From this point onward, we move beyond established physics into a speculative extension, the information gauge, or IG, perspective being explored by ThothSaem. The IG viewpoint describes the world not simply as a list of isolated objects, but as a network of informational relationships connecting events. It asks what information one event can transmit to another, which relationships remain invariant when an observer changes description, and whether a closed informational path can leave a phase-like trace. In such a picture, time may not be a river outside the universe pushing everything forward. It could emerge as the causal ordering in which distinguishable informational states are updated, together with the relational scale by which those updates are compared. A clock would not be a container holding time. It would be a physical system that forms stable correlations with another system. The past could then be understood not as a location that has simply disappeared, but as a set of constraints encoded in the present relational network. Even if a system returns to an apparently similar state after a cycle, its connections might retain a path-dependent residue. In IG language, such a residue could be investigated as a candidate informational holonomy. Memory would not be a copy of a past scene. It would be a relational difference revealing how the present state was formed. An attractive interpretation is not enough to create new physics. If IG merely renames phenomena already explained by relativity, quantum mechanics, and thermodynamics, it adds no predictive value. It must produce a distinct quantitative prediction. One possible testing ground is a relational quantum clock experiment. Two different internal clocks could be used to describe the evolution of the same system. Researchers could then ask whether a gauge invariant residual remains after changing the clock description. They could reverse the preparation order or the orientation of a closed control path, then subtract all known dynamical phases, bury phases, and environmental noise. Another test would prepare final states with the same energy and entropy through different informational paths. Does a small reproducible correlation phase remain where standard quantum theory predicts none? To become compelling, such a residue should obey a common coupling, constant or scaling law across different physical platforms. It cannot be rescued by adding a new arbitrary parameter for every apparatus. The falsification criteria must be equally clear. If the effect is explained by imperfect clocks, gravitational redshift, thermal drift, decoherence, or control pulse errors, it is not evidence for IG. If it disappears whenever the apparatus changes, or if every experiment requires unrelated fitting parameters, the hypothesis loses credibility. If increasingly precise measurements continue to agree with standard theory, the IG coupling must be constrained, revised, or rejected. This distinction matters. The philosophical sentence, time is relational, may be a starting point, but it is not a scientific conclusion. A theory must tell us which relationship to measure, how much the result differs from existing theory, and what observation would prove the proposal wrong. Now we can return to our first question. Does time really flow? Physics can say several things with confidence. Clocks measure proper time along their paths. Events possess causal order. In the macroscopic world, entropy increases in one overwhelmingly probable direction. Memories and records are formed along that direction. These are measurable features of reality. But physics has not directly measured a single cosmic present moving forward, a future that suddenly comes into existence, or time as an independent substance flowing past us. Our sense of passage may emerge from the combination of relativistic spacetime, a low entropy past, accumulating records, and the limited perspective of observers embedded within the universe. That does not make life an illusion. Quite the opposite. Even if time is not a river, change is real. Decisions alter our relationships with later events. Once a trace has been created, perfectly reversing it is extraordinarily difficult. A word or an action changes another person's memory and the physical state of the world. We may not possess time, but we can influence what information our passage leaves behind. Where is the person you were as a child? Perhaps that child remains as an event in space-time. Perhaps the child is compressed into correlations in your present body and memory. Under either interpretation, we cannot return and live the same moment again. The preciousness of life may come less from what time is made of, and more from the fact that our route through change is traversed only once. Perhaps time does not pass beside us at all. Perhaps we move through relationships of change, calling the path behind us memory, and the possibilities not yet connected to us the future. This moment may not be a universal blade of now cutting across the entire cosmos. Yet, the event in which you hear another person, choose one thought, and leave a small trace in the world is real. Does time pass through us? Or are we passing once and only once through a universe of change? If this journey changed the way you think about time, please subscribe and leave a like. This has been ThothSaem's Science Catch.